Hello hiers and welcome to lesson 7. We're going to look at a brand new calculation called bond enthalpy. It's my favourite calculation, you're going to love it. Before that though, as usual, we're going to do a wee starter. Okay, so I've got 4 questions. It's all about periodicity, yeah, remember that. Very important, the first 4 lessons we ever did. So question 1, what is meant by electronegativity? Question 2, explain why the sodium atom is bigger than the sodium ion. Question 3, we've got Al plus in the gaseous state going to Al3 plus 2 electrons. I want you to calculate what the delta H value is for that reaction. Okay, and question 4, why is the second ionization energy of lithium far greater than the first ionization energy for lithium? Okay, so I want you to pause the video just now. I want you to attempt the 4 questions. I'm going to go over them now. So very first question, what is meant by electronegativity? One of these definitions you just need to know. It is a measure of attraction that an atom has for bonded electrons. Okay, it's just one of those definitions you need to know. Okay. Question 2, why is the sodium atom bigger than the sodium ion? Remember when we talk about ions, write the electron arrangements out. So sodium is, the atom is 281, the ion is 28. Okay, so straight away that should be blatantly obvious why the atom's bigger, but let's go through the steps. Okay, sodium atom has 1 extra energy level. Remember, you have to be specific in that. Okay, so the sodium atom has 1 extra energy level. What does that mean? Well, the extra inner energy level, that provides a stronger shielding effect, okay? That weakens the force of attraction between nucleus and outer electrons, therefore the sodium atom is bigger, okay? We did that to death, you should hopefully be getting that, okay? Question 3, work out the delta H value for that equation there. It's all about ionization energy, so you need to be looking at page 11 of the data booklet. And if we look at aluminium, you'll notice in the question aluminium's already at Al plus, so the first ionization energy's already happened, so we don't need to include that. Okay, so if we look at aluminium, you'll see it just if I get my finger, my thumb on it, there's aluminium there. So we don't include the first one, but we add 1817 and 2745, we add that together and we should be getting plus 4562 kilojoules per mole. Why plus? Because ionization energy is an endothermic reaction. Okay. Question 4, why is the second ionization energy of lithium far greater than the first ionization energy? So remember what I said, write out the electron arrangements. Let's see what's happening. So the electron arrangements are like that. So it starts with Li, which is 2,1. The first ionization energy takes it to Li plus, which takes it to 2 electrons, and then the second ionization energy goes to Li2 plus, and that takes it to 1. So what does that mean? Okay, well, it means during the second ionization energy, the electron has been removed from a stable arrangement. So here, 2, that's a stable arrangement because it's got the same electron arrangement as the nearest noble gas, helium. So that's stable. We're removing an electron arrangement from that stable arrangement, and also the electron is also closer to the nucleus where it is pulled more strongly by the nucleus. Yeah, that electron there is in a different, is in a shell further away. Here, the electron's a lot closer, so the nucleus is pulling on that a lot harder. Okay, so self-mark your work, make sure you're getting the right answer. Remember, we need to keep on top of our notes, yeah, looking over our notes maybe 5-10 minutes a night just to make sure we're on top of it. Okay, right. So, as I said, we're going to look at bond enthalpy. It's a new calculation, my favourite calculation, as I've already said. We're just going to jump straight in, okay? Right. So we're going to make a wee note here, talk about what bond enthalpy is. So bond enthalpy is the energy required to break, you might have already guessed it, 1 mole of bonds of a molecule in the gaseous state. Okay, and that there, again, you can be asked it. It's came up, it's only came up once in the last 4 or 5 years, but it can come up. Okay, now I always find this one to be the hardest one because it's a combination of the two we've already learned, the ionization energy and the enthalpy of combustion. Remember, the definition of the first ionization energy is the amount of energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. Okay, enthalpy of combustion is the energy released when 1 mole of a substance is burned in excess oxygen. Bond enthalpy is the energy required to break 1 mole of bonds of a molecule in a gaseous state. Okay, you need to make sure you don't get any of those definitions mixed up. It's easy to do. Yeah, it's so easy to do. That's why you need to be looking over your notes. Right. Just carry on this wee note. So bond enthalpy values can be found on page 10 of the data book. Okay, so here is page 10 here. We've already used this page. Yeah, we've used that for our enthalpy of combustion. Yeah, that's our values there. We're now looking here downwards. Okay, so we're going to look at each one of these tables almost, and we're going to discuss what each one means, and then we're going to start doing a calculation. Okay, now you'll notice we've got bond enthalpies, and we've also got this one here called mean bond enthalpies. Okay, now mean from maths or any other subject really, you should know is just another word basically for average. Okay, so I'm going to give you the definition of mean bond enthalpies, and I'm going to talk about the difference between the two. Okay, so again, this is very important because this question actually got asked in the 2019 paper. So mean bond enthalpies refer to an average energy of a number of compounds. Okay, now bond enthalpies relate to one one compound / diatomic molecule. Okay, and what we mean by that, if we go back to our page here, you'll notice on the bond enthalpies HH, OO, N2, F2, Cl2, all of these are complete molecules. Okay, we can't fit any other atom on that because the valencies are all full. Yeah. Now, if we go to our mean bond enthalpies, we've got a carbon-to-carbon single bond, double bond, triple bond. These aren't complete molecules. okay, we could get two carbon-to-carbon double bonds in the same molecule, okay, and they could have different bond enthalpies. And all this mean bond enthalpy means is that it's the average between the two in a molecule, okay. CF, we could have multiple CFs in a molecule. What this value here is the average of all those CFs. Okay, so that's the difference between mean bond enthalpy and bond enthalpy. Okay? Right. So we're going to carry on. So molecules, in fact, let's change that. Okay. In fact, you know what? Let's change that again. So in chemical reactions, bonds are either made or broken. Okay, so in every chemical reaction we either break a bond or we make a bond. Okay, now what we mean by that, you should know from, well, first year really, reactants go into products. Yeah, now in order for the reactants to get converted into products, we need to break the bonds in the reactants. Okay, so we are breaking the bonds in reactants, and then what happens is new bonds, we are making brand new bonds. Okay, now don't worry if you're like, oh my god, what the hell is this? It will make more sense when we start doing the calculation. So what you need to know is that reactants undergo bond breaking and products undergo bond making. You need to get that into your head. Okay, now if we go for bond breaking, yeah, let's just go for a simple H molecule. Okay, now let's imagine this pencil is the HH bond. So we've got a H atom here on the right, we've got a H atom on the left. Now if we want to break this bond, what do I need to do? If I just hold this pencil like this, will the bond ever break? No. What I need to do is I need to put energy into that bond to break it. So I'm putting energy into it. Okay? Now, energy in to break bond. Now, if we're putting energy in, can you remember what type of reaction takes in energy? Okay, so if we're putting energy in to break, that is an endothermic reaction. Yeah? Now, if that's an endothermic reaction, you should know from ionization energy that the delta H is positive. Okay, and you need to know all three of them. Okay, so when we're breaking bonds, we need to put energy in to break that bond, and if we put energy in, that's endothermic, and if it's endothermic, that's positive. Okay, now if we go to bond making, yeah, so let's say we've got a H atom and we've got a H atom. Okay, so what's going to happen is these two H's are going to collide. Now, if we look at my fist again, we've got a H atom on my right hand, we've got a H atom on my left hand. Now, what happens, yeah, if you imagine my two hands as being, I don't know, two lorries that are carrying petrol, okay? Imagine that, two lorries carrying petrol. Now, if they're going at speed and they are driving towards each other and they hit each other, what's going to happen? Yeah, it's going to explode, okay? So the two lorries will come in and they'll explode, okay? And they'll release energy. And that's what's happening when we make a bond. So the two hydrogen atoms are going to come in and then they're going to release energy. So hit, release, okay? So when they do hit each other, okay, energy is released, okay? So we're getting a H bond like that. Energy is released, and hopefully you should know energy released is an exothermic reaction, okay? And if it's exothermic, that means the delta H value is negative, and we did that when we did enthalpy of combustion, okay? So it's very important that you understand the difference between bond breaking and bond making. So when we are breaking bonds, it's the reactants that we're breaking, and we're making the bonds in the products, okay? So for bond breaking, we need energy to break those bonds. That's endothermic, delta H is positive, okay? When we're making bonds, two hydrogens come in, they hit each other, energy gets released, okay? That energy released is an exothermic reaction, and that means delta H is negative, okay? So important. Now, how does that relate to what we're doing? We're building up to it, don't worry, we're building up to it. Now, let's look again. We're going to look at a couple of examples and then we're going to go straight into the calculation. So, again, we'll keep it simple. Let's just look at the H example. Now, if we go to page 10 in the data booklet, you'll see that HH has a bond enthalpy of 436. Yeah, so we'll write that. Has bond enthalpy of 436 kilojoules per mole. Okay, now this is the easy part. Yeah, if we break the HH bond, okay, so if we're breaking that HH bond, how do we break it? We need to put energy into it. If we're putting energy into it, that's endothermic. So that's got a value, yeah, it's got a value of positive. So the value is plus 436 kilojoules per mole. Yeah? Now, if we make a HH bond, okay, so the two H's hit each other, they release that energy, okay? If we release energy, that's an exothermic reaction, so the delta H is negative, so all we do is we put the negative in. Yeah, so if we make HH, the value is positive 436. If we make if we break HH, the value is positive 436. If we make HH, the value is negative 436. How easy is that? Yeah, so simple. Let's go to oxygen. Okay, so to break the value is what? Let's look at our data book. Where's oxygen? Here it is. Okay, 498. So if we want to break oxygen, it's positive 498 kilojoules per mole. Okay, if we want to make it, if we want to make a molecule of O2, the value, what do we do? Simple. It's negative 498 kilojoules per mole. Now this can get a wee bit more complicated, okay? But really, it's not that big a deal. Let's look at a molecule of methane. Yeah? What bonds does methane have? The only bond that it has is CH. Yeah? And if we look at CH, which is here, yeah, that's 412. Okay, so CH has a value of 412. Now, what you'll notice, it doesn't just have one CH bond. You'll notice that methane has 1, 2, 3, 4 CH bonds. So, have a wee think. What do you think we would need to do? Yeah, if one bond is CH is 412, 4 bonds, quite simply, is just 412 times 4. Yeah? And if we just, I don't want to do this in my head because I'll end up messing it up. If we times that by 4, that's 1,648 kilojoules per mole. Okay, so if we want to break 1 mole of CH4, we need to put in 1,648 kilojoules per mole. In fact, we'll try and squeeze it in. Kilojoules per mole. Okay? If we want to make, however, 1 mole of CH4, we get 1,648 kilojoules of energy released. Okay, and that's that. Okay, you have to, it's very important to count your bonds, and when we do this calculation, which we're just about to, you need to make sure you're counting your bonds. So important that. If we've got 1 CH bond, it's only 412. We've got 4, so we times that by 4. Simple. Now, let's do the last one. Water. Looks like that. It's an angular, bent shape, okay? You'll notice what type of bond does it have? It has 1 OH bond. Yeah? What is that? Let's look at our data book. Where do we see OH? There it is. It's written a wee bit different. It's HO, but it's still an OH, okay? That's 463. Yeah? So that's 463 kilojoules per mole. However, we don't just have 1 OH bond, we have 1, 2. Okay? So if we want to find out what 2 OH is, very simple, just 463 times 2. Okay? Now, that is 926 kilojoules per mole. Yeah? So, to break 1 mole of water, we need to put in 962 kilojoules of energy. Okay, if we want to make 1 mole of H2O, we get 926 kilojoules released. Okay, so that's why it's negative, because we're releasing that energy. And that's it. Yeah, see if you can do that. You're well on your way to understanding this calculation. Okay, right. I am aware that we're about 25 minutes in, so I'm going to start the calculation now. Okay, and I'm going to write a question. Just give me 2 secs here. I had a question up on my screen, but the screen's cancelled. Right, okay. So the question would look something like this. Using bond enthalpies, and that's your clue. The minute the question says using bond enthalpies, you should know, right, page 10 of the data booklet, let's do this calculation. So using bond enthalpies, calculate the enthalpy change for the following reaction. Okay, and this reaction here is going to be H2 plus Cl2 goes to 2 moles of HCl. And that's your question there. Okay, so we need to look at this and be like, right, how do we do this? Now, in chemistry, we love splitting our page. Yeah, it's what we do, we love it. Now, when we do this, it's very important that you split your page, and it's even more important that we split our page directly underneath the arrow. Okay, so we're splitting it into reactants and products. Okay, that is so important. Now, the next step you want to do, sometimes it's already done in the question for you. However, if it's not, you need to draw the molecules out. Okay, now H2, very simple, is just H bond H. Cl2 is Cl bond Cl. HCl is H bond Cl. Now, this is what you've got to remember. We've got H bond Cl, however, and I'm going to highlight this, we've got 2 moles of HCl. So what we need to do is we need to draw HCl out twice. Okay, and that's crucial. Okay, if you don't do that, you're going to be making mistakes. Now, once we've done that, once we've drawn the molecules out, I want you to split your page into breaking and making. Okay, now remember, the reactants, we're breaking them, and the products, we're making them. So breaking and making. Okay, if you want to, I'm just going to underline these just. So that's how we set up our page, like that. Now I'm going to use a different pen just to keep myself right. Now, in the break, always start with breaking. Yeah, start on the left. Now we need to write what is it we're breaking. Okay, so you can see by drawing it out, we're breaking a HH bond and we're breaking a ClCl bond. Okay, so you would draw that, HH, and how many are we breaking? We're breaking 1. So put a line through your bond like that. Okay, and that's very important, and it'll be even more important when the questions get harder. Okay, so draw a line through that. So that's 1 HH bond. How many Cl bonds? Just 1 Cl. Cl bond. Now a lot of people, if they don't draw the molecule out, they'll instantly think they've got 2 Cl bonds. Why? Because it's Cl2. Okay, make sure you draw your molecule out and you'll notice you've only got 1 Cl-Cl bond. Okay, and then this is where the data booklet comes into it. Put your enthalpy value in. Okay, so HH is 436 and it's breaking, so it's positive 436, and Cl-Cl is 243. So again, that's positive 243. Now, if we add that up together, I'm just going to quickly do this. That should be positive 679 kilojoules per mole. Okay, just double check that for me. It should be 679. Now, once we've done that, we move on to the making side and we do the exact same thing. Okay, what are we making? We're making a HCl bond. How many are we making? We're making 1, 2. Make sure every time you do these calculations, you're scoring out the bond. Okay, so we've got 2 HCl bonds. Now, if we look at our data book, HCl is 432. Okay, so because we've got 2 of them, we do 2 times 432. And what does that equal? That equals negative 864 kilojoules per mole. Okay, why is it negative? Because we're making it. When we make bonds, boom, we release that energy. Okay, and then once you've done that, you're pretty much there. Just draw a line, and to get your delta H, to get your enthalpy change, oh sorry, the question should be calculate the enthalpy change. Okay, so to get your enthalpy change, which is delta H, you have to do the enthalpy of the breaking, add the enthalpy of the making. Okay, now what you can do, because you don't want to be writing that out every single time, you can just write HBr plus HMA, just to shorten it down. Okay, so HBr is positive 679, yeah, and the making is negative 64. So if we add a negative, we're essentially just taking it away. So take away 864, and we should be getting a value of negative 185 kilojoules per mole. And that there is your answer. Okay, and what does that negative tell us? It tells us that this reaction overall is an exothermic reaction. Yeah, and that's it. That is how you do a bond enthalpy calculation. Right, I'm going to do one more example with you. So it's going to be the exact same question as before. So using bond enthalpies, calculate the enthalpy change of the following reaction. What reaction are we going to do? We're going to do CH4 plus O2 goes to carbon dioxide plus water, and if we balance this, you need to put a 2 there, 1, 2, and then put a 2 there. Okay, so again, start every bond enthalpy question the same. Underneath the arrow, draw a line. Now if the question is not drawing the molecules out for you, you need to draw the molecule out. Okay, so CH4 is just C, like that. Okay, now O2, remember, okay, and a lot of people forget this, O2 is that? It's a double bond. Remember, the valency of oxygen is 2, so it can form 2 bonds. Now, we've got 2 of them, yeah? So we need to draw 2 of them. So important, that. Carbon dioxide, again, this is another one that tricks a lot of people. Carbon dioxide actually looks like that. And we did that at National 5, okay? It looks like that. It's a linear molecule like that. And water is angular, and it looks like this. And remember, we've got 2 of them, so we need to draw 2 of them. Yeah, so important that you draw these right, because if you don't, you're going to mess up. Okay, now once we've done that, we split our page into breaking, making. Okay, breaking on the left because we break up the reactants, and making on the right because we make our products. Okay, now I'm just going to I just meant to underline them. Right, so start with the breaking first. What is it we're breaking? What bonds can we see? Well, I can see a CH bond, yeah? And I can also see an O double bond, O bond. Okay, now, CH, how many CH bonds do we have? Well, let's count them. 1, 2, 3, 4. So we've got 4 CH bonds. How many O double bond O's do we have? We've got 1, 2. Yeah, remember to score out your bonds. So we've got 2 of that. Now, if we look at our data book, page 10, CH is 412. Okay, so that would be 4 times 412. Okay, and then oxygen is 498. So that is 2 times 498. And again, I'm just going to pop this in the calculator to make sure we're not messing up. So it's going to be positive, because we're breaking it, 1648, and the other one is going to be positive 996. Okay, and what we need to do is we need to add these 2 together. So 1648 add 996, and we're getting positive 2644. Okay, and again, that's kilojoules per mole, obviously. Now, making. What bonds are we making? Well, I can see a C double bond O, yeah, and I can also see an OH. Now, how many C double bond O's can I see? I can see 1, 2. Yeah, remember, score out your bonds. So I can see 2 of them. How many OHs can I see? Well, I can see 1, 2, 3, 4. Like so. Yeah? Again, if we look at our table here, CO is 743. Okay? So that's going to be 2 times 743. And the OH, remember it's written HO, but it's still OH, that's 463. So we do 4 times 463. Yeah? Now if we do this in our calculators, okay, so 743 times 2, what are we getting? We are getting negative, remember, because we are making them, negative 1486. And we are getting 463, so put that in your calculator, we're getting negative 1852, and if we add these 2 together, what we're getting negative 3338. Yeah. And what do we do now? Just sort of underline our page, and we write out our enthalpy change. So delta H equals H breaking plus H making. Okay, so put our values in, plus 2644, and again if we add a negative number we just take it away. So plus 2644, take away 3338, and our value, let's just put that into our calculators, double check with me please, that should be negative 694 kilojoules per mole, and that's it. That's our answer. That's how you do these calculations. Yeah? Okay. Right. We are going to carry on this lesson on Friday. However, in the meantime, I'm going to put up a couple, just 2 questions. I'll put up 2 questions for you to do on your own. Okay? And then on Friday, we're going to start looking at this here. Okay, so we've looked at that table, we've looked at that table. We're going to look at the enthalpy of sublimation of carbon. Okay, right. Thank you.